Okay, we need to get started, so let's settle in and get going. So one announcement today that's in the notes that you can look at. Alpha Epsilon Delta Pre-Medical Society has a meeting Thursday in this room in the evening, so if you're interested in that, the information is in the notes for you. So today we're going to continue on with sort of a lot of different topics in Chapter 3. A couple of things before we get into it, though. First of all, remember that we are skipping, for now, Section 3.34. So if you guys follow along in the textbook, there's a section in there on what's called lattice energy and Born-Haber cycle. We're not going to do that until Chapter 7, so that part you can skip over for now if you're reading the book along with me. And then also, just to give you some advance notice about it, as you recall, the first exams is going to be starting February 18th, so that's about a week and a half from now, roughly 11 days or so. And so that you should be able to sign up on CASA. I haven't checked to see if they've opened up the calendar for sign-ups yet, but usually it's about 2 weeks in advance. Someone's nodding their head that they've already done it. So I encourage you to log on to CASA and sign up for a time to make sure you get one that works for you. And then also, there's going to be an exam review. That's going to be Friday. Obviously, it's outside of class time. It'll be 1 p.m. in this same room. These usually go an hour and a half, even a little bit longer than that. You're welcome to come late, leave early if you have to. If you cannot come to the exam review, it will be on YouTube, so you don't have to miss everything. And there's going to be a set of questions we'll go over, and I plan to post that by Monday, so you'll have a few days to go through those. Maybe even by Friday of this week I'll get it done. So there's going to be a set of 20 questions we'll go over, simulating the exam that you'll take. Not real exam questions, but very similar. And it's good for you if you're able to do those in advance, and then I will go through all the solutions during the review session. All right, so that's how that'll work, and I'll give you some more reminders about that since that is still over a week away. All right, so last time we finished up with some of the very beginning stuff in Chapter 3. Chapter 3 now we're talking about bonding, which is taking individual atoms and combining them to form chemical compounds and forming bonds between those atoms. The first step we talked about was ionic bonding. We're not going to give a lot of details about ionic bonding just yet. Essentially, all you need to know is what we did last time. So with ionic compounds, you can use the periodic table in many cases to predict which ions form, and then so you have metals that lose electrons, you have nonmetals that gain electrons, and so really ionic bonding is a transfer of electrons between nonmetals and metals. And once you have those positive and negatively charged ions, they combine in a ratio that cancels out all that charge or gives you a net charge zero species. So we talked about all that last time, how to predict which ions are formed, how to predict the compounds that form from them. Now this reminds me, remember that it's the metals that are going to lose electrons and form cations. So when sodium lost an electron, it was distraught and it went to the police station and it said, officer, I think I've lost an electron. He said, are you sure? And he said, I'm positive. So remember that one. And that's kind of, that would have fit better last time, but we're going to move on from that today. We talked about ionic bonding last time. We're going to come back to ionic compounds at the end of this chapter and learn how to name them, how to do the nomenclature for them, and we'll see, again, that section in 3.4 is about ionic bonding. We'll talk in more details much later on in the course about it. Today we're going to start with covalent bonding. So in ionic bonding, you're transferring electrons between the two atoms. One of them is losing electrons, one of them is gaining. It's always going to be a metal with a nonmetal. Covalent bonding is when two atoms come together and share electrons. So they're not actually transferring electrons between each other, but they're sharing them. And this typically, as we'll see, is going to involve two nonmetals with each other. So things on the right side of the periodic table tend to form covalent bonds with one another. And we'll see why that is in a little bit. So when you have two atoms coming together to form a bond, the question is, why does this happen at all? What are sort of the energetic consequences of doing this? Because remember, in chemistry, what things want to be able to do is minimize their energy. They want to go to the lowest energy state possible, and forming a bond in most situations, or in many situations, is a process that releases energy and stabilizes the system. So what we're going to do is we're going to work on this diagram right to left. And what we see here is the x-axis, the horizontal axis, is the distance between the two atoms. This, I believe, is for H2, or roughly quantitative for H2, but other atoms, you're talking about, again, sort of picometer scales, those sort of small atomic scales. And so at the very right of the diagram, the two atoms are far apart, and there's no interaction between them. So they just behave as free atoms. They're not interacting in any way. And so if we measure the relative energy to this, it's going to be 0. There's no energy of interaction. Now, however, once they start to get close to each other, so here I'm showing they're getting closer and closer as we go right to left, you get to a situation where the electrons from one atom are going to start being attracted to the nucleus of the other atom. You're going to have new proton-electron attractions, so electron-nuclear attraction, again, with the protons in the nucleus. And so in that situation, you have new attractive forces. Remember, when a positive and a negative charge attract with each other, when they interact with each other, that tends to release energy or be a negative potential energy as is conventionally defined. So the energy starts going down. You start getting to negative potential energies. And then at some point, you're going to get to the point where you formed a stable covalent bond, where basically the electrons in the atoms are close enough to each other that two electrons are shared between the two atoms. They completely are, and they're going to be, as we'll see later on, interacting with both nuclei simultaneously, not just belonging to one atom or the other, but actually shared by the two and interacting with both of those nuclei. So you get to a minimum at some point, but then if you get them too close to each other, so if you start pushing the atoms and squeezing them closer and closer, you start to have electron-electron repulsion or proton-proton repulsion if the nuclei start bumping into each other. That starts to take over and the energy goes back up. All right, so you're going to, again, get to some minimum, but then if you try to force them too close together, the repulsive interactions between the electrons that are shared or not even unshared electrons and the nuclei take over. So you get to this minimum point here, which is where we would say we have a stable covalent bond. That's where, again, the electrons are shared, and you've minimized the energy by maximizing the attractions between those electrons and the two nuclei that they're shared between. Now we're going to talk more in detail about the shape of this well, but as we'll see, this well has a certain depth to it, a certain energy energy of interaction along the y-axis, as well as a certain distance where this minimum occurs. And the shape of this well and the positions of that minimum correlates with certain properties of the bonds. And so we're going to talk about what those properties are and how they relate to this diagram coming up next. So it's not going to look quantitatively, it's not going to look exactly the same for every bond. As I said, this one roughly approximates what hydrogen would look like if you had two hydrogen atoms coming together to make a covalent bond. But other types of atoms bonding with each other would have wells that have still the same basic shape, this sort of concave type of plot with a minimum somewhere at some distance and some energy, but where that minimum occurs and how wide the well is, I guess, those all are determined by certain properties of the bond, some of which we will talk about. All right, so let's talk about those properties then that are important for this diagram and for other things we're going to talk about. So one of them is bond energy. This is also known as, aka, bond strength. So we'll use that terminology sometimes. Or sometimes, to be a little bit fancier, we'll call it bond dissociation energy. So let me write that word again. Dissociation. So bond dissociation energy. In this last terminology here, bond dissociation energy, BDE as it's abbreviated, that's the most descriptive because it tells us this is the amount of energy required to break that bond apart, to dissociate. Dissociate means to break something apart. And so that's what this energy value refers to. Now here's the part that's a little bit confusing for us at this point, but don't worry about this detail too much. These are going to be defined for 1 mole of a bond. Now many of you probably already know what a mole is. If you don't, that's okay. but a mole is basically a large collection of bonds. It's not one single bond, it's a huge number of those bonds to make it a more measurable quantity or more, one that's more familiar for human scale measurements. All right, so it's the amount of energy required to break 1 mole of a bond in the gas phase. The numbers, again, are not going to be important for most things we do. We're more interested in comparing bond energies between different types of bonds. And so what then the reaction would look like is if you have 2 atoms, A and B, bonded to each other, again, just like most of these energy quantities that we've started defining, last time we talked about a couple with ionization energy and electron affinity, they're always defined in the gas phase. And the bond association is the amount of energy that's required to do this process. So to take the 2 bonded atoms and completely separate them from each other. Again, still leaving atoms in the gas phase. And this change in energy is what we refer to as the bond association energy, or just bond energy sometimes, for that bond AB. So we'll put AB as a subscript, and that's always going to be a positive number. So if you form a bond, it always takes energy to break that bond apart. So it's always a positive number. And so then if we go to this diagram here and find this minimum point in the diagram, if we extrapolate over to the y-axis as best as we can, that number, which for this one would be about 100, 200, about 300, this would be the negative of the bond association energy. All right, so again, this diagram is defined for the energy of interaction between 2 atoms. Bond association energy is the opposite process, where you're ripping 2 atoms apart. So how deep this well is, in other words, the magnitude of the difference between where they're not interacting and where they've formed a stable bond, that y-axis value is going to give you the bond association energy. Okay, so that's how that relates to the diagram we drew. And then the other important parameter is bond length. This is the distance between the 2 nuclei when they're bonded, when the 2 atoms are bonded together. Now, we already introduced this on some level because really it's bond distances that are often used to determine atomic radii experimentally. So you have 2 atoms that are bonded to each other at some stable distance. Let's say they're 2 different sizes, A and B. They have different atomic radii. And if we want to know the bond distance, we just measure the distance between the 2 nuclei. And that distance will be called the bond distance or bond length for this AB bond. So it's always, again, 2 atoms bonded to each other, and the distance between those 2 nuclei we always measure as a function of where the nuclei are located. That's going to give you the bond distance. One thing that we're going to talk about is the idea that bond distance is inversely related. So we'll introduce the idea now and talk about it in more detail as we go along. It's inversely related to bond energy. So these 2 key parameters of a bond sort of track in opposite directions with each other. So if you have a smaller bond distance, you tend to have a larger bond energy, and vice versa. Longer bond distance gives you a smaller bond energy. So that's kind of one thing that's going to be important to keep in mind. And then if we go back to this diagram here, the bond distance would just be where this extrapolates to the x-axis. So where that minimum lies above the x-axis is the bond distance for this particular covalent bond. All right? So those are the 2 key properties of covalent bonds, really of any bond, but we're going to talk about it mostly for covalent bonds and how they relate to each other and how we can sort of see them in this diagram that we started with. All right, so going on then, there's some other things we have to keep in mind as that also relate to bond distance and bond association energy, and a big one of those is called bond order. So as we introduced, a covalent bond is formed when 2 atoms come together and share 2 electrons, but in many situations it's possible for those atoms to share more than 2 electrons. So the bond order is defined as the number of bonding pairs between the 2 atoms. We're still primarily talking about sharing pairs of electrons, so it's always going to be even number of electrons that are shared, but the number of those pairs that's shared is going to be given as the bond order. All right? So if you have a single bond, the nomenclature we use is single, double, triple. Single bond means bond order is equal to 1. and that means you have one shared electron pair. So an example of this would be when hydrogen forms a bond with itself, two hydrogen atoms come together. Remember, hydrogen only has one electron, so if two hydrogens come together, they have two electrons. They can only share two, that's the most they can do. So hydrogen, when it bonds with another hydrogen, makes a single bond. We draw that either as a single solid line between the two hydrogens, or there's some, especially in sort of old school sources, you'll see them drawn as dots, where each electron is drawn individually. So this is two different ways of drawing a single bond, which would just be one shared pair of electrons. Double bond is, as the name implies, a bond order of 2. And this would be two bonding pairs then. So now, instead of the two atoms sharing 2 electrons, they share 4 electrons between each other. So we'll learn how to predict these bond orders later today and next time, but essentially, if oxygen forms a bond with itself, it doesn't just share one pair of electrons, it shares 2. And so we draw that as 2 lines between the 2 oxygens, indicating 2 shared electron pairs. Or if you wanted to draw out all the individual dots like people used to, you would draw 2 sets of dots and make it 4 total electrons that are shared between the 2 atoms. All right, we're going to talk more about drawing structures later today, but essentially bonds are represented by lines, individual electrons represented by dots, and so sometimes you'll see this one on the left with the lines is much more common than the dot nomenclature nowadays, but you should be familiar with both. And then the highest we'll ever see in the molecules that we deal with in this course is a bond order of 3. So there are some exotic things that have bond orders of 4 or even 5, I think is the record. But in the types of things that we'll deal with, the highest bond order you'll see is 3, and that involves then 3 bonding pairs, or what we call a triple bond, as I've indicated here. Nitrogen forms a triple bond when it bonds with another nitrogen, and so that would be a way to draw it with 3 lines. Nope, just 3 lines. I tried to. So that's one way to draw a triple bond, or again, you can draw it as dots. It gets a little bit cumbersome with 3 pairs of dots, but it's the same thing, telling you the same thing. Okay, so that's how we indicate triple bonds, which are bond order of 3. Now, why bond order is important is, if you think about it, as we increase the bond order, we're sharing more electrons between the atoms. We have more interactions of the nucleus with those electrons, and so that's going to bring things closer together. So in general, if you have a higher bond order, that results in a shorter bond, which would then correspond to a stronger bond or a larger bond energy. All right, so that just adds in one more relationship to the one we discussed on the last slide, which is that we said that if the bond is shorter, it tends to be stronger, and the bond order affects that, whereas you increase the bond order, you tend to decrease the bond length and increase the bond energy. The more shared electron pairs you have, the more difficult it is to rip those 2 atoms apart from each other. And I think that should make intuitive sense. So those are the key properties of a covalent bond. A big thing that we're going to do in this course is compare bond properties between different bonds. We'll get to that in a second, but first let's just do one quick example problem. So I gave you 2 of these bond potential energy diagrams here. Now we want to know the bond energy and the bond length for the weaker of the 2 bonds that are shown. All right, so remember that weaker means the smaller bond dissociation energy. So that's what we're looking for with these two diagrams here. Remember, the smaller dissociation energy is going to be the one that has the shallower well, the one that doesn't go down as far from the origin, the y equals 0 position. So this plot here is not as deep as this plot. So this is going to be our weaker bond. So we're going to focus on this one. And we go down and extrapolate to the x and y axis to get the distance, and I have to try to draw my lines straight, which is not always easy. And that's what we get. So that's going to be the weaker bond, is this one, because its well is not as deep as the other one. All right, so if we extrapolate, we want to get the bond energy. That goes to the y-axis. The y-axis is potential energy, as is clearly labeled here. And so the potential energy would be, for the bond is minus 250. The bond association energy is just the absolute value of that, 250. And then the bond length, we extrapolate to the x-axis. That's going to be 150 picometers. So choice D is correct. If we compare that to the red trace, we see that the red trace, the bond energy is closer to 300. Okay, so remember the one with the smaller bond energy is the weaker bond. That's why we chose the blue trace to look at, and that gives us these two values. All right, so that's not going to be a huge thing that we do, but you might see problems here and there that deal with these types of diagrams and how to interpret them and what they mean. So review that a little bit. But then the bigger thing that you guys are going to be asked to do is to compare bond lengths. So we're going to give you a set of 3 or 4 and say rank them from longest to shortest, or rank them from strongest to weakest. So if we're doing trends in bond length, which then are inverse to the trends in bond energy, so you can, the comparisons, the factors that influence these comparisons are the same for both. The first thing you want to look at is bond order. That ends up being, in most cases, the more dramatic effect on bond distance is going to come from bond order. So if you're comparing atoms that are, especially ones that are all in this, similar parts of the periodic table, the atomic radii of everything is very similar, like we have here. CF, CO, and CN. If we go to the periodic table, we see that those are all going to be very similar to each other in terms of their location on the periodic table. So it's going to be carbon bonded to nitrogen, oxygen, fluorine. All of these are in the same row of the periodic table. They all have 2p valence electrons, all similar sizes. We know last time that they're not exactly the same size, but we have atoms here that are all fairly similar. And so if we're comparing these, well, the first thing we want to look at then is bond order. So that's kind of the first thing we look at. And so if we're comparing these 3 bond distances, we would expect the one with the highest bond order to be the shortest. So the C triple bond N is going to be the shortest bond distance, followed by the C double bond O, followed by the C F distance. All right, so if you're comparing bond orders, things that have the same atoms bonded to each other or very similar ones that are all kind of in the same part of the periodic table, don't even think about anything else, just look at the bond order and compare it that way. However, in many cases, it is sometimes important to either consider separately or also consider the sizes of the atoms themselves. So let's say we're comparing 2 bonds to each other and the bond order is the same. How do we deal with that? So in this example that we're going to work through next, we have CF, CCl, and silicon chlorine bonds. All of them are single bonds. They're all drawn with one line between them. So how do we compare bond distances if the bond orders are the same? And so the second criterion to look at, which sometimes you'll have to look at both of these to be honest, to really rank all of the choices we give you, the second one is the atomic radii of the bonded atoms. All right, and we talked last time how to compare atomic radii based on the location in the periodic table. Atomic radius increases as we move down a column. It decreases as we go left to right. And essentially when you have 2 atoms bonded to each other, 2 small atoms are going to make a short bond and 2 large atoms are going to make a long bond. That I think also should be fairly intuitive. So now let's compare these 3. Very often when we're doing rankings or comparisons, it's helpful to just do 2 at a time, not try to look at all 3 together. So let's do CF versus CCl and figure out which one of these will we expect to be longer or shorter than the other. Here we're comparing bond lengths. So if we go to the periodic table, we see that both of those bonds have carbon in them, so the atomic radius of carbon is constant. And in one of them, carbon is bonded to fluorine, and in one of them, carbon is bonded to chlorine. So between fluorine and chlorine, F and Cl, which one is larger? Chlorine, because we're going down. So that means you would expect the bond between carbon and chlorine to be longer than the bond between carbon and fluorine. If it's bonded to a larger atom, you expect them to be farther apart from each other. So between these 2 then, the CCl bond is going to be larger. And then if we compare CCl, let's do 2 at a time as I said, to SiCl, it's also helpful to compare bond distances that have 1 shared atom between them. So we see that both of these involve chlorine, just like both of these involve carbon. So when you're comparing bond distances, it's sometimes helpful to find ones that have one of the atom the same, and then you only have to worry about the relative radius of the second atom that it's bonded to. So if we do carbon chlorine and silicon chlorine, the same type of argument. Carbon chlorine, silicon chlorine. Carbon and chlorine are, we expect to be longer or shorter than silicon chlorine. I heard some of both, but maybe I didn't phrase the question very clearly. So silicon is larger than carbon. It's below carbon. So we would expect the bond between silicon and chlorine to be longer than the bond between carbon and chlorine. Again, the effective radius of chlorine should be about the same for both, so it's a function of which of these two is larger. Silicon is larger than carbon, so the bond between silicon and carbon should be longer. All right, so when we compare those two, we see that carbon chlorine should be shorter than silicon chlorine, and so the ordering for these is going to be exactly in the order I gave them to you. With carbon fluorine being the shortest, carbon chlorine being in the middle, silicon chlorine being the longest. So when you're comparing things that have the same bond distance, the same bond order, and you want to know which one has smaller or larger bond distances, it's going to be a function of the radii of the atoms that are bonded to each other. And as I said, sometimes you have to do a combination of the two. Some comparisons would be difficult. So, is a carbon-sulfur double bond longer or shorter than a carbon-oxygen single bond? That's a tough comparison because the atoms are different size and the bond order is different. But we'll give you comparisons that should be pretty straightforward and should have an unambiguous ranking or answer, whatever we're trying to ask you in these. All right, the next thing we have to talk about for covalent bonds is a parameter called electronegativity. All right, so we introduced covalent bonds as the idea that two atoms are sharing the electrons with each other, but the unfortunate situation is that the electrons are not always shared, or not unfortunate, but the reality of the situation is that electrons are not always shared equally. Okay, it's not always that each atom completely shares the electrons totally with the other one, but sometimes there's an unequal sharing. So, for example, in an example in your everyday life, I spent the first 19 years of my life sharing a room with my twin brother. Okay, so we're the same size, so we share the room exactly equally. But if a little brother and a bigger brother are sharing a room, the bigger brother is probably going to take more of the space than the little brother and be kind of a bully and take that from him. So the same thing happens in bonds. They don't always share things equally. They have two electrons that are shared, or more than two electrons if it's a multiple bond, but they don't always share those electrons exactly equally with each other. And that's the situation, and that's what electronegativity allows us to predict, is which of the atoms is hogging the electrons more than the other. All right, so the definition of electronegativity is the relative ability of a bonded atom to attract the shared electrons. So the larger the electronegativity, the more it's going to attract the electrons to itself, and the more unequally the electrons will be shared between those two atoms. All right? This was introduced by Linus Pauling, who spent a large part of his career at Caltech in California, and one of the most famous, I would say one of the most famous American chemists in the 20th century. And he came up with this scale for electronegativity, which is still largely the one that's used and preferred today. And it's a relative scale, so you don't have units associated with this. That's just a comparative scale. So it's a relative scale derived by Linus Pauling. And the highest electronegativity on the periodic table is fluorine. It is helpful to remember that fluorine is the highest, just because as in problems where electronegativity comes up, that's going to be something important to remember in many cases. Its electronegativity value is 4. So the scale is not huge. It goes to 4 is the highest electronegativity. And then the lowest is the opposite corner of the periodic table. So fluorine is in the top right. The opposite corner of the periodic table, the bottom left, has the elements that have the lowest electronegativity, and those would be cesium and francium, which are tied with electronegativities of 0.7. All right, so it's not a huge scale, as we said. It ranges between 0.7 and 4, but it does depend on the location of the element on the periodic table, as we'll cover here in a second. Now, how is this defined precisely? So it's basically what you're doing here is if you have two atoms bonded to each other, A, B, the expected bond dissociation energy is going to be the average of AA and BB. So if the electrons were shared exactly equally in a covalent bond, if you had two atoms A and B bonded to each other, you could predict their bond energy by just taking the dissociation energy of A bonded to itself, B bonded to itself, and averaging the two. The reality is that's not usually true, and so I'm not going to go through the details of this, but basically by looking at the difference in the actual bond dissociation energy versus this expected bond dissociation energy, that's how Pauling derived his scale. So the electronegativity, the unequal sharing of electrons, actually makes bonds stronger than you would expect if the electrons are shared totally. And by comparing those numbers and normalizing them in some way, he was able to get this relative scale for all the different atoms on the periodic table. All right, so that detail is not important, but just kind of a little background of where these numbers come from. So let's look at then the periodic trends. This is the last periodic trend we'll cover. It's a very simple one, as you'll see, but it only applies to atoms that are bonded to each other. So electronegativity is not a property of a single atom by itself. It's a property of an atom when it's bonded to something else. And so the trend for electronegativity goes the same way as ionization energy and electron affinity. It's actually related to those two in some sense. Although, again, it applies to a bonded atom and not an individual atom. And it increases as we go up and to the right. All right? So we said that fluorine over here is the most electronegative atom. These ones down here are the least electronegative, and so the trend increases up and to the right. And there's not really any exceptions you have to worry about. It might not be a perfectly smooth trend, but we're not going to hold you responsible for any exceptions in the electronegativity trend. So it increases across a period. It decreases down a group. And so this would be the order of increasing electronegativity. So it's the same trend as electron affinity, which is closely related to electronegativity. We said that electron affinity is the sort of desire of a single atom to acquire an extra electron. Electronegativity is the desire of a bonded atom to draw electrons to itself. So those two are closely related to each other. Again, they're different, they're defined differently, but they do have that relationship, and that's why the trend would be roughly the same. Now, there will be, likely you'll see on the homework assignments, problems that say, rank these in order of electronegativity, where we just compare a group of elements and say which one's the most, least electronegative, those types of questions that you'll see a lot in this chapter. But the importance of electronegativity is it allows us to determine what is referred to as bond polarity. So this is one last bond property we need to talk about. We talked about bond length, we talked about bond dissociation energy, and now we have what's called bond polarity. And this is a situation when you have atoms with different electronegativities that bond to each other. So when two atoms with different electronegativities form a bond, the bonding pairs are shared unequally. I should say, to be a little bit more precise, whether it's one bonding pair or more than one bonding pair, they would be shared unequally. Okay? So how do we indicate this when we're drawing out, chemical bonds and comparing them and stuff? So there's two ways to do this. So if we have hydrogen and fluorine bonded to each other, again, you don't have to memorize the numbers, but the electronegativity values for hydrogen is going to be 2.1. Fluorine, as we said, has an electronegativity of 4.0. It's the most electronegative atom. And what happens is that the electrons are going to be shared unequally, and they're going to have more electron density near fluorine than you are near hydrogen. So the atom that has a larger electronegativity is going to pull more of the shared electrons towards itself, and it's going to be sort of slanted in that direction. Now, because of that, you have what's called a dipole, which is sort of a region of positive charge and negative charge. It's not completely +1 and -1. You haven't transferred the electrons, but they're shared unequally. So the two ways we indicate this are with sort of this dipole picture here, which has a plus sign and then an arrow pointing. And the arrow points towards the more electronegative atom. That's one way of indicating polar bonds. Or the other way, which I think is probably more common and in my mind more helpful, is you draw the bond between H and F, and you indicate a partial negative charge on the more electronegative atom. Again, that's going to be drawing more of the electron density towards itself, and a partial positive. So this little letter that I drew is the Greek letter small delta, lowercase delta, and delta means partial in this context. Okay? So this is the more common way of drawing it, I would say, and the more helpful in my opinion. So you have a partial negative charge on the more electronegative atom. It's not like an ionic situation. Remember, in ionic compounds, we completely transfer electrons and we have full positive and full negative charges. Here, it's just a partial positive and partial negative. It's an imbalance of charge, but not complete transfer of electrons. The electrons are still shared, just not very equally. So you have a partial negative charge on the more electronegative atom. And so these are two ways of indicating bond polarity. So this is what bond polarity means. It's an unequal sharing of electrons that causes an imbalance in the charge between those two atoms that are sharing electrons. And then what we need to move on to next then is how we compare all right, my notes are disorganized and I lost something. All right, well, I'm going to have to wing it on this slide because I don't have my notes for this one. So here we go. All right, so the importance of difference in electronegativity. Last slide on this, I'm just missing one of my note pages, but that's okay. We'll go through this. So delta electronegativity is the difference in electronegativity. That's going to be, if we have two atoms A and B bonded to each other, it's electronegativity of A minus electronegativity of B, or I guess more accurately, the absolute value between those. So in other words, it's how different are the two electronegativities of the atoms that are bonded to each other. And a perfectly covalent bond, you would have the difference in electronegativity is 0. So if the two atoms have the same electronegativity, which rigorously is only true when the same atom is bonded to itself. But if you have no difference in electronegativity, then you have a perfectly covalent bond, and that means the electrons are shared equally. And we call that a nonpolar bond. All right, so again, the time when this is rigorously true is when it's the same atom bonded to itself. So when hydrogen bonds to hydrogen, they have the same electronegativity, they have the same draw for those shared electrons, and so they share them perfectly equally. It's almost like a tug of war, you can think about it. If you have the two atoms sort of, trying to draw the electrons towards themselves, if they're pulling equally in both directions, the electrons are going to be shared perfectly equally, and you have no bond polarity. The charge distribution is completely symmetric. All right, but in this other situation, if you have your difference in electronegativity is not 0, so in other words, the two electronegativities are different for the two bonds, this is going to be what we call a polar bond. And that would again be the situation where you have unequal sharing of electrons. And we sort of, at the beginning of this chapter, we kind of classify the types of bonds as sort of two black and white categories. Ionic bonds where electrons are transferred, and then covalent bonds where electrons are shared. The reality is you don't really have a distinction between those. It's just a continuum which ranges from nonpolar covalent on one side and ionic on the other. Yes?
So it's like a certain percentage of the time a bond is covalent, and then in a polar bond there's a certain part where it is ionic, like a 17% or whatever.
So the question was, which is a good one, is am I trying to say that a certain percentage of the time the bond is covalent and a certain percentage of the time it's ionic? I wouldn't think about it necessarily as percentage of time, but we have what's called percent ionic character. So if you have a difference in electronegativity that's non-zero, you would have some percent, a non-zero. Sorry, it froze for a second. It's still frozen. Might be my pen is gone. Let's see. All right, good. We're back. All right, so if you have a difference in electronegativity that's non-zero, you have a non-zero then percent ionic character. All right, so then kind of conventionally what we say then is if the difference in electronegativity is, let's say, less than 2, and this would be two nonmetals bonded to each other, we still classify that conventionally as covalent. Again, these are kind of arbitrary distinctions because there is no real difference between covalent and ionic. It's just the extent to which the electrons are shared or unshared. If the electronegativity difference is greater than 2, which would be the situation if a nonmetal and a metal bond to each other, we still conventionally classify those as ionic. But the point here is that there's really a continuum. So you would have, I'll draw this down here because I ran out of room, you would have sort of nonpolar covalent as one extreme, where you have perfectly shared electrons. You'd have polar covalent sort of in the middle, where the electrons are shared but unequally. And then the opposite extreme would be ionic, where the electrons completely get transferred between one atom and the other. But there's no fundamental difference between these types of bonds. It's just a reflection of how equally or unequally the electrons are shared between the two atoms. Okay, so we still use covalent and ionic terminology. It's still a nice, simple way to think about it. It's not wrong to think about it that way. But the reality is, you have polar covalent bonds. They're sort of on the way to ionic bonds, just not completely there, not completed electron transfer. Okay, so any questions on that concept? So the point of the matter is, when we want you to rank bonds in terms of polarity, you look at the difference in electronegativity between the two atoms, very often by referencing their positions on the periodic table and seeing which one are farther apart from bottom left to top right. And then that difference in electronegativity tells you qualitatively how polar the bond is. And the terminology percent ionic character is sort of synonymous with polar bond. The larger the percentage ionic character, the more polar the bond is. All right, so that's kind of the last thing we had to talk about with bond properties. The last thing we'll do in this section is we're going to use one of these bond properties, which is bond strength or bond energy, to calculate the change in energy for a reaction. All right? So delta E for a reaction is going to be the change in internal energy. We're going to come back to this more in detail in Chapter 7. But for now, we're just going to introduce it at a very basic level. So when you do a chemical reaction and you change, some collection of elements and compounds into another collection of elements and compounds by rearranging the bonds, we talked at the very beginning that the chemical reaction is just rearranging bonds. You're breaking bonds, you're forming new bonds. In that situation, you're going to have some amount of energy that's either added to or released from the system, because we talked at the very beginning that bond energies are all different from each other. And so if you're forming different combinations of bonds, the likely situation is that the bond energies on either the reactants or the product side are going to be different from each other. And so you have a difference in energy between reactants and products. So that's what this delta E is. It's the change in internal energy when reactants convert to products. So for any chemical reaction. As we'll talk about later on, you can think of this almost as heat. So as the reaction happens, it's kind of a function, related to how much heat is either added to the system or released from the system when the chemical reaction occurs. Now, how do we use bond strengths to calculate delta E for a reaction? So what we're going to do is we have a set of reactants, and they have their own bonds that are associated with them. And we're going to first break all the bonds in the reactants. So remember that breaking bonds requires energy input. Now I should point out that this is not really how chemical reactions occur in most places. When we do a chemical reaction, we don't break every single bond and then form all the new bonds. But this is how we would calculate or think about it. We take all the reactants, we break every single one of their bonds, it figures out how much energy that requires, which is always going to be a positive number because it takes energy to break bonds. So it requires energy input to break the bonds in the reactants. Remember, when we're writing a chemical equation, that's going to be the left side of the equation, is the reactants. This I do feel like is a little bit out of place. That's one of the unfortunate aspects of this textbook, is that they reorder the chapters in kind of a haphazard way. So we haven't talked about a lot of this, but we do want you to at least be able to understand this aspect of, so you're doing chemical reactions and you're breaking the bonds in the reactants, and then we take all those atoms that we've now generated by breaking all the bonds in the reactant side, and we recombine them in different ways to make the products. So in most cases anyway, a different quantity of energy is going to be released when we form the new bonds in the products. And so because it's releasing energy to form bonds, for this step, the formation of the bonds, the delta E will be negative, less than 0. When the atoms form new bonds in the products. However many there are. Now, whether you internalize all of those concepts or not, what you're going to have to be able to do in this section is do the calculations. And so what we're going to ask you to do is typically calculate delta E. And so what you're going to do is take the sum of all of the bond energies for the reactants. So in a typical problem, we'll give you all of the reactant bond energies. You don't have to know those numbers or come up with them in any other way. You take the sum of those and you subtract then all of the bond energies for the products. All right, a new Greek letter for you, which is capital letter sigma, too many squiggles. Capital letter sigma, which if you've taken math courses, you know means the summation of everything. So we're summing all of the bond energies for the reactants. We're summing all the bond energies for the products, and we're subtracting those two quantities. Where again, BE is equal to, as the abbreviation for bond energy, also bond association energy, which are kind of used interchangeably. Okay, so that's the equation. If you just know how to use this equation, you're going to be, good for most of this section of the chapter. Now, occasionally we'll have you solve for one of the bond energies of the reactants of the product. So again, there could be different unknowns in the problems, but it's really just one equation for you to worry about and know how to use. So let's give an example of this. So we have this reaction here, where we have this molecule, which is called formaldehyde, reacting with pH3, which is called phosphine, and then we're forming this product here. So again, the details of the reaction aren't important. We just want to be able to calculate the bond energies. So I gave us some extra space for work because this does require a lot of arithmetic. So remember, the way that we approach this problem is we're going to take all of the bond energies on the reactant side, add them together. We're going to take all of the bond energies on the product side, add them together, and then once we have those two numbers, we just subtract the two. That's typically, I think, the easiest way to organize your work on this. So looking at the reactant side then, the key to doing this is we have to count up the individual bonds that we have. So we do have to have accurate structures drawn. We don't know how to do that yet, but that's coming next. And once you have an accurate structure, you have to count up how many bonds there are. You have to take into account whether they're single, double, or triple bonds, and make sure you get the right bond energy that corresponds to that. So for this first reactant here, we have one type of bond we have is CH, but we see that we have two of them. We have a carbon bonded to that hydrogen and a carbon bonded to that hydrogen. So two CH bonds. And so what we're going to do is we're going to take 2 times the bond energy for carbon hydrogen. So CH bond energy is given here, 413 kilojoules per mole. We'll just leave out the per mole part because it gets confusing for now. And it's just going to require 826 kilojoules to break those two carbon-hydrogen bonds, and we do it for the other ones as well. So this reactant also has a carbon-oxygen bond. It is important to make sure we use the right number. So it's one carbon-oxygen double bond in this reactant here. And we see that we're given two different numbers for CO bonds. One of them is for the double bond, one of them is for the single bond. As we said, double bonds have much larger bond energies, as you can see here. So we need to make sure that we use this number on the reactant side because it is a carbon-oxygen double bond. So we just have one carbon-oxygen double bond, but the bond energy is going to be 745. So again, all the bond energies that we need are given to us, but we have to make sure we use the correct ones, especially in cases where we have different bond orders as part of this. All right, and then finally we have another reactant, PH3. We haven't covered how to draw structures yet. I should have given it to you in more detail. PH3 is going to look something like this. We'll see how to draw the structure later on. But we only have pH single bond energy given to us, and there's going to be three of those. Phosphorus bonded to three hydrogens. Even if you didn't draw the structure, that's pretty obvious from the formula. So we also have three pH bonds in our reactant side. So remember, we're summing up both reactants in this case. There's two reactants on the left side of the arrow, so we have to account for all the bonds that are in both of those. So we have three pH bonds, and those each have a bond energy of 320 kilojoules. And so that gives us 960 for that contribution. All right, so the part we have to then finally do is we get the sum of the bond energies for the reactants. Is going to be these three numbers added together, 826, 745, 960, and we get 2,531 kilojoules. So that's how much energy is required to break all of the bonds in the reactants. Two carbon-hydrogen bonds from this reactant, one carbon-oxygen double bond from that reactant, and three phosphorus-hydrogen single bonds from the PH3. So that's the reactant side, and then we go and we do the product side. The product there's only one product. We have to account for all the different bonds that are present here. So if we look at CH bonds in the product, it still has two. Carbon bonded to hydrogen, carbon bonded to hydrogen. So two carbon-hydrogen bonds are still present in the product side. We didn't form or break any CH bonds in net. So it's going to be 2 times 413 kilojoules. That's the CH bond energy. So that's the contribution from those. If we go up to the product, we see that this product has still a carbon-oxygen bond, but it's no longer a double bond, it's now a single bond. Okay? So this carbon-oxygen bond in the product is indicated as a single bond with one line in between. So we're going to use this number here, 358, for the carbon-oxygen single bond. All right, so I'm going to have to scroll back and forth so you guys are going to get whiplash here. But we have one carbon-oxygen single bond in the product, which has a bond energy of 358 kilojoules per mole. Our product also has a new type of bond, which is OH. So we formed a bond between oxygen and hydrogen, an OH single bond. And so we're going to have to use this last number here, 467, which is the OH bond strength. And there's one of those here, that bond there. So we have one OH bond. Which is going to be 467 kilojoules from our list of bond energies that were given. All right, two more. We'll go back up to the product. We have to make sure we count all the bonds. This has a carbon-phosphorus bond. So again, looking at from the perspective of carbon, we have two bonds to hydrogen, one bond to oxygen, and one carbon-phosphorus single bond. That's also a new bond that's formed. That's going to correspond to this bond energy here, 264. So our one carbon-phosphorus bond has a 264 kilojoule bond energy. And then finally, the last type of bond we have in our product, we still have two phosphorus-hydrogen bonds. We've lost one of them, but two of them are still there. Phosphorus-hydrogen single bonds, same number that we use on the reactant side, 320. So two phosphorus-hydrogen single bonds, but because we have two of them, again, we have to double that number. So 320 kilojoules for each phosphorus-hydrogen bond, but there's two of them, so we have to double the number. And so now we can sum up all of these. These are all of the bond energies in the products. And so the sum of the bond energies for the products is going to be just all of those added together, which I got 2555 kilojoules. Okay, so that's how much energy then is released when all of the bonds form on the product side. And then finally, the delta E then is going to be those two numbers subtracted, the sum of the bond energies for the reactants minus products. And so we saw that when we calculated it for the reactants, it was 2,531 kilojoules. We're going to subtract the bond energies for the products, which is 2,555. And so then our delta E is calculated to be negative 24 kilojoules. So a negative number, relatively small in magnitude, and delta E can be positive or negative, so it's not always going to be negative, it's not always going to be positive, it's going to be either or. And that's how we do it. So it's a lot of arithmetic. Now some of you might try to get cute and do, we noticed that not all the bonds are breaking, right? We preserved the carbon-hydrogen bonds, we preserved two of the phosphorus-hydrogen bonds. So you could just do this as a difference between, which bonds are formed on the reactant side and broken, but it gets, I think, confusing to do that and keep track of all that. So I do think even though it's a lot of arithmetic, the simplest way is to just count all the bonds individually, break all the bonds on the reactant side, form all the bonds on the product side, take your two numbers and subtract them. So these problems are going to be fairly time-consuming if you have to go through all this. This one was probably, fairly advanced even for what you'll see, a lot of different bond energies to account for, but the process is always the same. Sum up the reactants, sum up the products, and subtract the two. All right, and again, it's one of those things, the more you practice it, the simpler it will seem. All right, any questions on that topic? Because we're going to now move on to something totally different. So any last thoughts on that? All right, again, I probably won't see you if you raise your hand, so just shout it out if you have something. Now we're going to move on to a topic called Lewis structures. We probably won't get all the way through this today, but this is, again, another major part of Chapter 3. So we're talking about formation of covalent bonds and how, and we saw in that example problem there that you can have, molecules that have many different atoms involved, bonded in different ways. And so we're going to learn now how do we actually draw the structure. So if we give you the formula for a compound, a covalent compound specifically, how do we predict what the structure of that's going to be? Where are the single bonds? Where are the double bonds? Which atoms are bonded to each other? All that good stuff. So what are Lewis structures? They're going to be 2D representations of molecules. As I said, we're primarily going to do this for covalent compounds, which are combinations of nonmetals. We're not going to do terribly complicated ones in most cases. But what these structures show is that they show all of the valence electrons. All right, and this is very important for us to be able to do because, as we'll get to in the next chapter, Chapter 4, once you have a Lewis structure for a molecule, you can make predictions about the three-dimensional shape of that molecule. You can make predictions about how the bonds are formed in that molecule and what that means in terms of some of its properties and its chemical reactions, all kinds of things. So we have to start with Lewis structures, though. It's very important to be able to do this efficiently and correctly. So the Lewis structures contain each different atom or each different element represented by its atomic symbol. So each atom in the structure just has a letter that represents its atomic symbol. We've already seen some Lewis structures, so these shouldn't be totally foreign to you, but the key here is to learn how to draw them ourselves, how to produce a Lewis structure. So we're going to use atomic symbols for each different atom in the structure. And then conventionally speaking, again, there are two ways to do this, but the way that you'll always pretty much do it in this course is we're going to show the bonding pairs as solid lines. So you just draw a line for each bonding pair. Again, there can be single or multiple bonds. Sometimes you'll have more than one bonding pair between atoms, but each one is going to be shown as a solid line. Now, something we have not had to deal with yet are what are called lone pairs. So these Lewis structures are going to show every single valence electron in the whole molecule, and not all of those are going to be shared between atoms. Some of those are going to remain as unshared electrons, or what are called lone pairs or non-bonding pairs. And these are going to be shown as pairs of dots. So each pair of dots would represent one non-bonding pair of electron. And so what these lone pairs or non-bonding pairs are they are valence electrons that are not involved in bonding. So they still just belong to one of the atoms in the molecule. They're going to be localized on one atom. And most of the Lewis structures you will do are going to have a combination. You're going to have some bonding pairs, some non-bonding pairs, and the structure will show all of those. And we're going to learn again how to decide which, how many bonding pairs, non-bonding pairs do you actually have. All right, so that's what lone pairs are, and they're going to be drawn as dots in these structures. So they are valence electrons, but they do not actually form bonds with other atoms. So what we're going to go through today, and probably not get all the way through, but most of the way through, is a step-by-step process for drawing Lewis structures. Now this is going to seem kind of laborious, like, oh my goodness, 5 steps, I have to remember all of them, but I'm going through it sort of slowly and deliberately on purpose to help you guys get used to all these steps and know why they're important. The more and more of these that you do, the more and more that you practice, a lot of these steps are going to become second nature and kind of get agglomerated together, and you can do them a lot quicker than I'm going to do with these first few examples. But I want you to understand the process, and if you understand and use this process correctly, you'll be able to draw just about any Lewis structure correctly. So the first step you have to do, and there's no shortcut around this, and if you skip this step, you're already dead in the water basically, is you have to add up the total for each atom. Okay? So you have to add up the total number of valence electrons. So we have to know how many valence electrons are we dealing with in this molecule or ion. So you add up the total for each atom. We have to remember to account for the number of each atom that there are. So the chemical formula will tell us how many of that atom is in the structure. For example, if we have CO2, carbon dioxide, make sure you account for the fact that there are 2 oxygens. Each of those oxygen atoms is going to contribute as valence electrons. So when we're counting valence electrons, don't forget that little detail about the chemical formula. And so that's going to be the first step, is to add up valence electrons. Now we know from the periodic table, we'll review this here in a second, that we can use the location in the periodic table, the group number, to tell us how many valence electrons there are. Now one of them we don't have to even think about. So for the element hydrogen, how many valence electrons does hydrogen have? So this is always going to contribute 1 valence electron. And when you're drawing Lewis structures that involve hydrogen, hydrogen is the simplest one to deal with. Every Lewis structure with hydrogen, you're always going to just have 1 single bond, and that's it. So hydrogen in any sort of covalent compound forms 1 single bond, and you're done. So you draw 1 single bond of hydrogen and you stop there. All right, so if you guys come to office hours and you're drawing Lewis structures and I see you draw double bonds of hydrogen, or I see you put lone pair electrons on hydrogen, every time that happens a small piece of me dies. So please don't do it. Just 1 bond of hydrogen and stop. That's all you have to do. Now other elements is more complicated, as we'll see. But the first thing, as I said, we have to count the valence electrons, which we know how to do already. So for the S and P block elements, we're primarily going to be doing P block elements for Lewis structures, non-metals, as we said. There are a couple we'll talk about that have S block elements, but basically you just take the outermost NS and NP electrons. So those together give you how many valence electrons. And like we said, the periodic table that we have is numbered in sort of the old school AB nomenclature. And so if you just read off the group number for these S and P block elements, that directly tells you the number of valence electrons. You don't even have to necessarily think about the full electron configuration. You just have to look at the group number, and that'll tell you how many valence electrons you have. And remember, this is only for the outermost highest N values. So the core electrons that we have, all of that sort of core noble gas configuration electrons that we represent in full electron configurations, those core electrons do not participate in bonding, and they're not going to be shown in Lewis structures. Only the valence electrons, those that are in the outer shell. And then what about charges? So we are going to also draw Lewis structures of charged ions, what we call polyatomic ions. And so we have to remember to account for those charges. If you have negative charge, you have to add electrons to your total. And then if we have a positively charged polyatomic cation, we subtract electrons for each positive charge. All right, so that step will usually come at the end. You'll add up all the valence electrons from the atoms, but then if there's a net charge, positive or negative, you have to adjust that total to account for the overall charge that you have. All right, so that's how we total up valence electrons. And so as we go through all of these steps, we're going to do it for 3 representative Lewis structures, PCl3, NO3-, and IF5. I chose these 3 because they all illustrate something a little bit different about drawing Lewis structures, so they'll, as we go through, we'll get we'll be able to see all these different things that can come up as we're drawing and going through these steps. All right, so if we do PCl3, we have phosphorus and chlorine. We have to add up the number of valence electrons from each. So we have 1 phosphorus atom, and if we want to know how many valence electrons it has, we again go to the periodic table. P is in group 5, so how many valence electrons does it have? Remember, it's going to be the S2 and the P3 together, so all 5 of those are counted as valence electrons. So it's going to have 5 valence electrons for each phosphorus. For chlorine, we have to remember that we have 3 of them, and how much does each chlorine supply? If you have a periodic table in front of you, you can start it out. 7. It's in group 7 of the periodic table, S2P5 configuration. So we have 7 from each chlorine. Only the outermost valence electrons matter. So we have 5 from phosphorus, a total of 21 from chlorine, and then when we add the 2 together, we get 26 electrons. Okay? So this PCl3 molecule that we're going to draw the Lewis structure of will have 26 electrons when we're all said and done. And it's important to account them because as we're going through the steps of drawing Lewis structures, we don't want to put too few or too many electrons into our structure. Exactly 26 will go in. All right, NO3-, we'll count the electrons for this one. 1 nitrogen. Nitrogen is right above phosphorus, also in group 5. So that's going to give us 5 electrons. 3 oxygens. If you forget where oxygen is, it's right next to nitrogen, so it's going to be in group 6. So each oxygen contributes 6 electrons. But there are 3 of them, so don't forget that. And then this one, unlike the last one, also has a net negative charge. So we have to account for that negative charge by adding 1 more electron to the total. So this one is going to have a total of 24 electrons. All right, 5 plus 18 plus 1, 1 extra for the negative charge. Most of the Lewis structures we do, you'll have even number of electrons. It's a little bit hard to deal with odd number of electrons in this type of approach, but if you get an odd number of electrons, double check to make sure that that's actually correct. So this one comes out to 24, 26, and the last one, IF5. Iodine and fluorine are both in group 7, so each of those atoms is going to contribute 7 valence electrons. They're from different subshells. It's going to be the 5s and 5p for iodine. It's going to be the 2s and the 2p for fluorine, but they both have 7 valence electrons total. Okay? So 1 iodine with 7, and 5 fluorines that each contribute 7. And so that gives us a total of 42 electrons. All right, so that's the very first step in drawing a Lewis structure. We have to add up the total number of valence electrons. We should already know how to do that, but it's good to practice and get very proficient at it because it's a key first step that you cannot live without. All right, then the next step, once we know how many electrons there are, is to start arranging the bonds. And the first thing we do is we take the least electronegative atom and put it in the center, and we draw a single bond to the other atoms. Now, in almost every case, it's going to be very obvious what your central atom is, the one that goes in the middle. It's usually the one that comes first in the formula. It's usually the one that there's only one of. We'll see some slightly more complicated ones later on. But for these 3 that we're starting with, the central atom is going to be the first atom listed, and it is also typically the less electronegative of them. So phosphorus is less electronegative than chlorine. So again, phosphorus is to the left of chlorine, so it's less electronegative. Nitrogen is less electronegative than oxygen, so it'll go in the center. Iodine, less electronegative than fluorine, so that'll go in the center. But again, as I said, in most cases, just look at the formula. If you have one atom surrounded by multiple other atoms, that one atom is going to be your central atom. So we put that in the middle. Remember, for PCl3, we're using 26 valence electrons as we counted, and we're going to start by putting phosphorus in the center and drawing 3 single bonds, 1 to each chlorine. Okay, so that's going to be the first set of bonds that we draw, and it's helpful as we do this to keep track of how many electrons we've used and how many we have left. So remember that each bond is 2 electrons. It's a shared pair of electrons for each of those. So we've drawn 3 bonds in. That means we've used up 6 of our electrons. So in PCl3, we still have 20 electrons left. We need to figure out what to do with. That's going to come in the later steps in this process. All right, but we start with just single bonds to the outer atoms. NO3, we again do the same thing. 3 single bonds, 1 to each oxygen. Helpful to indicate that there's a negative charge by putting a little bracket with a minus sign. And we're going to have, again, keeping track of how many electrons are left. We started with 24 valence electrons for NO3 minus. We've again formed 3 single bonds in this structure, so that's a total of 6 that we've used up. So it is helpful as you go along to keep track of how many electrons you've used up, how many you have left. So we still have 18 electrons in NO3 minus that we have to figure out what to do with. So again, we're going to come next in that. And then finally, IF5. We started with 42 valence electrons for IF5. We put the iodine at the center, and we're going to draw single bonds to every single fluorine. All right, so that's always going to be the first step in the process, is to draw single bonds to every single outer atom. And so in this case, we have 42 to start with. How many have we used? We formed 1, 2, 3, 4, 5 bonds. Each bond is 2 electrons. So that takes up 10 of our valence electrons. We still have 32 left to distribute elsewhere. Okay? So that's going to be the first step. Draw single bonds to all of the outer atoms. I guess it's step 2 as I have them numbered. But once you start drawing the structure, that's the first thing you're going to do. All right, next thing is we have to distribute the remaining electrons as lone pairs or non-bonding electrons. So we have 20 electrons left for PCl3, 18 for nitrate, NO3 minus, 32 for IF5, and we have to distribute those as lone pairs. But the question is, do they go on the outer atom? Do they go on the central atom? Some on each? How do we know where they go? So there's 2 steps. First, you're going to complete the octet of all of the outer atoms. So we're going to introduce something new called the octet rule here. So we're going to complete the octet of all outer atoms with lone pairs. Again, remember, we don't do this with hydrogen. We only do it with other things besides hydrogen. Hydrogen just forms 1 bond, no lone pairs. But we're going to complete the octet. And what the octet rule says is that for each atom in the structure, ideally the number of bonding plus non-bonding electrons should equal 8. So each bond counts as 2 electrons, and then that atom should have a total of 8 around it from some combination of bond and non-bonding electrons. All right, so you want each atom in the structure to have 8 electrons surrounding it from the bonds that it forms, as well as from any lone pair electrons that belong to it. So once we add the lone pairs to the outer atoms, then if we have any leftover electrons go on the central atom. So we complete the octets of the outer atoms first, and then however many we have left go on the central atom as lone pairs still. Now, as we'll see, probably not today, but next time, these lone pairs are not always going to stay lone pairs. Sometimes as we evaluate the structure, we have to convert some of them into bonding pairs. But initially, this is how we're going to arrange them. We complete the octet on the outer atom by putting in enough lone pairs to give each of those 8 electrons, and then we add whatever remaining electrons, whatever leftovers we have, go to the central atom. Now, I'm going to give you a couple more considerations about the octet rule that are going to come up. So the first thing is that we have this thing called the octet rule, but it's not really a hard and fast rule. It's kind of like the rule that I have of don't text in class. I know you guys break it all the time. It's okay. And the same with the octet rule. It gets broken all the time, but there are, in most situations, that it does apply. All right, so atoms with greater than 10 electrons, or greater than 10 protons, I guess, in other words, third row of the periodic table, these ones can expand their octet. That means it is possible for atoms in the third row of the periodic table or beyond to have more than 8 electrons surrounding them. So it's not always going to be exactly 8, and in some cases it's going to be greater than 8. Now what we should point out is that this is only going to happen at the central atom. You're never going to have outer atoms that have more than 8 electrons. The outer atoms will always have 8 electrons. Unless they're hydrogen, they'll have 2. But if you have a central atom, it is possible to go beyond 8 electrons if the central atom is greater than atomic number 10. So sodium or anything past that on the periodic table. If you have the opposite situation, the atomic number is less than or equal to 10. Now, neon doesn't form compounds, but I guess it would still fall in this category if you did. So that'd be neon or anything before neon on the periodic table. Again, Z is the atomic number. Anything with atomic number less than or equal to 10 will never exceed the octet. Okay, so that's an important thing to keep in mind. Those cannot have more than 8 electrons. So for the first 2 rows of the periodic table, the octet rule will never be exceeded. There are a couple of cases where it will be violated. As I said, and I'll write it down here to be clear, only the central atom will expand its octet if that's necessary. And there's 2 elements on the periodic table besides hydrogen that typically do not have complete octets in their Lewis structures. So we'll see some with beryllium. That tends to have 4 valence electrons around it. And we'll also see structures with boron B, which is the next one. Those tend to have 6. So these 2 elements we should be familiar with. They always, or not always, but almost always have incomplete octets. Okay? All right, so that's the situation with the octet rule. For the outer atoms, we're typically going to have exactly 8 electrons around them. For the central atom, it could be less than or greater than 8, depending on the situation. Very often it will be 8, but that's the one that's going to more frequently violate the octet rule. So finally, let's just do the last step here, and then we'll close off and finish it next time. So for PCl3, as we said, there's 26 valence electrons total. We started with single bonds to each chlorine. And the next step is then to add lone pair electrons to the outer atoms to make sure that each of them has 8. So right now, each chlorine has 1 bond to phosphorus. So that's 2 electrons for each chlorine. We have to add 6 more to complete the octet. So each chlorine is going to get 6 lone pair electrons to complete the octets of all of the outer atoms. That's the first thing we do with those extra electrons. And then if we count up, we're going to get good at counting by 8s in this section. Each chlorine now has an octet, so there's 8 electrons here, 2 from the bond, 6 from the lone pairs. 8 electrons, 8 electrons. 3 times 8 is 24, so how many do we have left? So we have 2 electrons left, and remember that any leftover electrons go on the central atom. So we are also going to put 1 lone pair on the central atom because there's still 2 electrons left to finish this off. So that's all of the valence electrons for PCl3. If we do NO3 minus, this one has 24 valence electrons. So when we start with single bonds to each oxygen, that's still 2 electrons for each oxygen. We add 6 more to complete their octets. With a negative charge. And if we evaluate how many electrons we've used now, we have 3 complete octets, 3 oxygens, each with 8 electrons around it. So that's going to be all 24 of our electrons. All right, so we don't have any more lone pair electrons to put in the central atom. As we'll see next time, we're not done with this structure, but we don't put any more electrons into it because we've used all 24. We stop there. And then for IF5, we have 42 electrons. We started with single bonds to each fluorine. Now we have to draw a lot of dots because we're going to complete the octet of each fluorine atom. Again, 6 more electrons to complete the octet because each of these has a single bond so far. So we have 5 octets completed now. 5 times 8 is 40. So how many electrons do we have left? So in this case, we also have 2 leftover electrons. So we also have to put 2 on the central atom as a lone pair. All right, so that takes care of all the valence electrons. Next time we'll see how we evaluate these structures and see if there's any additional features we have to add, like multiple bonds and things like that. So we'll come back to that next time, and I'll see you then.